Hi everybody. In this video, we're going to integrate sine x times cosine x, the quantity raised to the power of 6. For this integration, we have a few different approaches at the different part of the integrals. We can apply directly u substitution inside of the parentheses and expand it to the 6th power and integrate each term one by one. You can pick your u as sine x or cosine x. So this is one approach. Another approach is to start with double angle identity. Or another approach is to apply integral reduction. I would like to go double angle identity because it is straightforward and simple. Let's begin. Let's remember what the double angle identity for sine of 2x. So we have three different kind of double angle identity for sine of 2x, but we are going to utilize this one because it appears in our problem sine x times cosine x. So we know that sine of 2x is equal to 2 times sine x cosine x by the double angle identity. Now let's divide both sides by 2. So sine of 2x over 2 is equal to sine x cosine x. This is exactly what we needed because it appears in our problem. Now we're going to substitute sine x cosine x by sine of 2x over 2. So our new integral will be sine of 2x over 2 raised to the power of 6 dx. At this point, we are going to distribute power into each term. So our integral will be sine 6th of 2x over 2 to the 6th dx. 2 to the 6th is 64, and 1 over 64 can be pulled to the front. Now we're going to apply u substitution for 2x. Let u be 2x, so du will be the derivative of 2x, which is 2 dx. And if we solve for dx in this equation, it's going to be 1/2 du. Now we're going to place everything into this integral. So we have 1 over 64 integral sine 6th of, instead of 2x, we're going to substitute u, and instead of dx, we're going to write 1/2 du times 1/2 du. And we can pull this 1/2 to the front. So 1/2 times 1 over 64 is 1 over 28. At this point, you can apply integral reduction. So if you go this method, or at the beginning I mentioned, if you go u substitution, or the way I do double angle identity, you get the answer in different forms. All the answers are correct. Your integral works for all of them. But the appearance of the answer might be different in 3 different methods. Now let's continue where we were. Here, my plan is to divide break sine into squared form, so I can apply half angle identity. So what I would like to do is 1 over 28 integral sine squared of u raised to the 3rd power. So 2 times 3 is 6, so this is equal to sine 6th of u. Now we're going to substitute sine squared of u with our half angle identity. Let's remember what the half angle identity was. Sine squared of x is 1/2 times 1 minus cosine of 2x. So whatever the angle is here is doubled here. So we have u in our argument, it's going to be 2u. Our new integral will be 1/28 integral, instead of sine squared of u, 1/2 times 1 minus cosine of 2u to the third power. We can raise 1/2 to the third power and pull it to the front. 1/2 to the third power is 1/8, and 1/8 times 128 is 1024. So what is left inside is 1 minus cosine of 2u raised to the third power. Here we're going to do cubic expansion utilizing Pascal triangle. So on the third expansion of Pascal triangle, our coefficients are 1, 3, 3, and 1. Since it is a minus b term, it's going to be negative, positive, negative. So we start like this. We start positive, negative, positive, negative. Here our a term is 1, and our b term is cosine of 2u. Our coefficients are 1, 3, 3, and 1. So a term cubed, which is 1 cubed, is 1. And b term to the 0th power, anything to the 0th power, is 1. And we have negative sign in between. So 3 times a to the second, which is 1 to the second, is 1. And b to the first power, which is cosine of 2u. And we have plus sign. 3 times a to the first term, which is 1, b to the second power, which is cosine squared of u, cosine squared of 2u, and minus 1 times a to the 0th is 1, and b to the cube is cosine cube of 2u. Let's clean up here. 1 times 1 times 1 is 1, minus 3 times cosine of 2u, plus 3 times cosine squared of 2u, minus cosine cubed of 2u. So we're gonna replace this with cubic expansion. So this is our final cubic expansion. So let's rewrite everything in terms of our cubic expansion. We have 1 minus 3 cosine of 2u plus 3 cosine squared of 2u minus cosine cubed of 2u du. Now we're going to separate each term into separate integrals, and we're going to attack each integral one by one. So we have 1/1024 in the front, integral of 1 with respect to du, minus integral of, we can pull 3 to the front, cosine of 2u, plus 3 integral of cosine squared of 2u, minus integral of cosine cubed of 2u, again du, and du here. Now let's observe one by one. We know how to integrate this. Here our plan is to use half angle identity. Whenever you have cosine squared or sine squared alone, we use half angle identity to integrate. And half angle identity for cosine squared of x is 1/2 times 1 plus cosine of 2x. Again, whatever the angle is here, doubled here. If you had here 2x, it would be 4x. If you had here 3x, it would be 6x here. Let's go back to our plan. So here we're going to use half angle identity, which is going to be 1/2 times 1 plus cosine of, this is 2u, so we have to double it, which is going to be 4u. And here our plan is to break cosine cube into cosine squared of 2u times cosine of 2u. And then apply here Pythagorean identity and u substitution. Since we have u here, we're going to use v substitution. Now we know our plan. Let's apply. One over 1024. Integral of 1 with respect to u is u. So we integrated the first one. Minus 3 times. Integral of cosine is, we can utilize this table. So in this chart, if you go to counterclockwise, you get the antiderivative of each trig functions. If you go to clockwise, you get the derivative of each function. And antiderivative of cosine that we are integrating here is positive sine. So sine of 2u times, we have 2u, so a chain rule, times 1/2. It's going to be 1 over a. Whatever the coefficient in front of variable is 1 over a. So times 1/2. So this integral is done. Next one, we're going to apply half angle identity. Plus 3 times integral of 1 plus cosine of 4u. 1/2 times 1 plus cosine of 4u. And let's continue. Minus, let's do this integral in the end. Let's take care of this 3. Okay, we have 1024 u minus, let's distribute, let's pull 1/2 to the front, 3 over 2 sine of 2u plus, we can pull 1/2 to the front, 3 over 2. Okay, integral of 1 with respect to u is u, so 3 over 2u plus 3 over 2. Antiderivative of cosine is positive sine, so sine of 4u times 1 over 4 by the chain rule, or you can use this table, 1 over a times sine of ax. Okay, we have taken care of first 3 integrals. Let's clean this up, write in the simplest form, and then attack on the 4th and the last integral here. U minus 3 over 2 sine of 2u plus 3 over 2u plus 1/4 times 3 over 2 is 3 over 8 sine of 4u. And we have minus cosine cubed of 2u minus integral of cosine cubed of 2u du. Let's check it. Yes, that's correct. Okay, we copied correctly. Now we're going to take care of this integral. As we said, we're going to break cosine into squared and cosine form. And we're going to substitute cosine squared of 2u with Pythagorean identity. Pythagorean identity is sine squared of x plus cosine squared of x is equal to 1. And if you solve for cosine here, it's going to be 1 minus sine squared of x. So we're going to substitute that with 1 minus sine squared of x, which is sine squared of 2u in our problem, times cosine of 2u du. Now we're going to apply another substitution. Let's call it v substitution. So let v be sine of x, sine of 2u. So dv will be the derivative of this. Derivative of sine is cosine, positive cosine, times inside function, times 2. So 2 cosine of 2u. Derivative of sine is positive cosine. And du, and if we solve for du here, du will be dv over 2 cosine 2u. Now we're going to place everything into this integral. So it's going to be integral of 1 minus, instead of sine, we're going to substitute v in our problem, because we did v substitution here. Whatever the letter you call it, we do that substitution. Since we used u substitution before, not to confuse it, I used v substitution. So it's going to be v squared and cosine of 2u, and instead of du we solved here, dv over 2 cosine of 2u. As you see, cosine of 2u's cancel out, and if we simplify, we get 1 minus v squared, and we have 1/2 here that we can pull to the front. Now we know how to integrate this. The antiderivative of 1 with respect to v is v, and we have 1/2, we can directly multiply. Since it is negative 1/2, because we had negative sign in front of the integral, let's carry that too. So it's going to be negative 1/2 v, and negative 1/2 times negative v squared is positive, and antiderivative of v squared is 1/3 times v cubed, and we have 1/2 in front that we multiply, which is going to be 1/6. So 1/2 times 1/3 v to the third. Okay, so this is our simplest form of the integral, the last integral. Now let's copy everything and then simplify. So I would like to copy paste, so we're going to be faster. So this is what we got so far. Okay. plus c. So let's simplify and write it in the simplest form. But we have to bring u and v back. We said u was equal to 2x, and we said v is equal to sine of 2u. Yes. Okay. One over 1024. Instead of u, we're gonna write 2x minus 3 over 2 sine of 2u, and instead of u, we have to write 2x. 2 times 2x is 4x. Plus 3 over 2 times 2x is just 3x. Plus 3 over 8 sine of 4 times 2x is 8x. Minus v is sine of 2u, and u is 2x, so it's going to be sine of 4x. So instead of v, we're going to write sine of 4x. Negative 1/2 sine of 4x plus 1 over 6 sine cube of 4x plus c. Okay, this is our final answer. If you wish, you can distribute 1 over 1024 into each term one by one, and then expand, leave your answer in that form. Or you can leave your answer in compact form, as I did here. I'm going to leave the answer in this form. You can leave in whatever form you prefer. And if you apply different methods I have mentioned above, like integral reduction or use substitution in the beginning, you might get your answer in different form. Your answer is appearing different than what I have here. But your integral is still correct for any computation. I hope this video helped. Thank you very much for watching.